Hello, my name is Felix Kremse, and the title of my presentation is Preclinical Dosimetry Analysis using the Imalytics Preclinical software. And I'm here in Germany for my company, Kremse IT GmbH in Aachen. Our software is already used worldwide at more than 100 sites, and here are some example customers in the academic field, but also the industry, and we are happy to work with different industry partners. Our software is easy to learn. You can become productive in one day, and we have a YouTube channel with 84 tutorial videos, and the tutorial datasets are also installed with the software. Our software is available for Windows, Mac OS, and Linux. It runs on workstations and laptops, and we recommend an NVIDIA GPU for large datasets. We also have affordable group licenses. And our software is compatible with all devices. It loads anything with voxels, DICOM, Nifty, Analyze, even the old Siemens Invion files. Now I will talk a bit more about dosimetry and the required analysis. There were recent successes with lutetium-177 PSMA therapy. In the image you can see a human scan of a patient with a lot of metastases and tumors all over the body, which got reduced after a few treatments of this lutetium therapy. But you can also see that there's substantial uptake in other organs like the kidneys, the liver, but also here the salivary glands. And this uptake causes some side effects. The imaging here was performed using a companion diagnostic here with gallium-68 PSMA, but with SPECT you can also image the lutetium directly. These successes, but also the remaining side effects, are motivation for more research. In preclinical research, you typically work with mice, and your scanners provide a calibrated image, for example, with the unit of megabecquerel per ml or kilobecquerel per ml. Then this data set can get converted to a biodistribution image with our software with the voxel unit of %ID per ml. With our dosimetry tool, which I'll show you later, you can convert this into a dose rate map. Then you can perform organ segmentation for each time point to generate the dose rate curves for each organ or lesion. For our dosimetry tool, we are leveraging published Monte Carlo dose point kernels. In this nice publication, they published 2,174 dose point kernels for different radionuclides. Here you see a visualization of such a dose point kernel. And this is used in a convolution operation in 3D to generate the quantitative dose rate map. We validated our software with clinical data. Here from this paper, we found published example datasets from a Siemens SPECT-CT scanner. And in this publication, they compared two different voxel-based dosimetry software tools, and our software generated similar absorbed radiation dose values for different organs and tumors. We are also happy that recently the first paper was published in preclinical research by the group of Carolyn Anderson in Missouri. Now I'll show you how this works in practice. Let's look into the Imalytics. The first step is typically to pre-process your image data. Now I'm opening here the data set with 3 mice. I'm loading in the PET as overlay. And here we have 3 mice. And I can change the windowing settings. And now this data is typically cropped per mouse. I can crop now one mouse here. This crops the PET and the CT. And here you can see the PET better. And then you can adjust the metadata. Here, for example, enter the injection amount for this particular mouse of the 3 mice. Then you can save the cropped CT and PET as DICOM files. You can click undo to go back to the 3 mice and crop the next mouse. So you can quickly sort your data on an individual mouse level, because the analysis is typically performed per mouse, not using the 3 mice. When you have sorted the data in parallel folders, you can have them here for one mouse. This is one folder for each time point. So this mouse, M1, was scanned 4 hours after injection, 24 hours, 48 hours, and 72 hours. We can now load one data set here, the CT, and we can also load the SPECT. And you can visualize this in 3D. You can set your windowing settings for some range that you prefer. And now with our batch mode, you can go through the time points. Here to the next time point. This is 24 hours after injection. And now you can see here there's accumulation in the subcutaneous tumor. We can go to the next time point, 48 hours after injection. And you see here there's even more uptake in the tumor. And in the third time point, 3 days after injection, you can see declining signal here in the tumor, but also in the kidneys and the liver. With our software, you can convert the SPECT image into a %ID image. I will just load it here. And this can get further converted into a dose rate map using our dosimetry tool. Here you can select an isotope. This can be the same isotope that was used for imaging, or you can choose a different one. So you can image with a PET companion diagnostic, then select a compatible compatible theranostic isotope. I will just select lutetium here and click apply, and the software now performs the convolution with the dose point kernel and generates a dose rate map image. The unit now is gray per second. This can be done for all the time points. I'm just loading the data that I generated already. And now it is time to generate an organ segmentation. I can show you how this is done on one example here. I will segment the tumor. So I will zoom in a bit here and use our scribble tool and add a class tumor. And now I'm delineating the tumor here in a few slices. So I'm basically providing a wireframe in a few slices. And then the software connects it when I press this button here. Now I can slice through and check where it is okay and add further annotations. This only takes a few minutes and I can segment the tumor in a sufficient way. Around 10 annotations are typically sufficient. Then I can accept this, and now we have a 3D segmentation here. I can also smooth it, and now I can compute the uptake here in the tumor. Or in this case, the radiation, the absorbed radiation dose here. I will load now some segmentation that I have prepared here, and we have a few more segmentations. Here we have the lung, the liver, the kidney, the tumor, and a muscle. We now have this for all the organs. We have this for all the time points, and I can go through the time here. This is 24 hours after injection, 48, and 72 hours after injection. I'm going back to the first time point, and now I can use our dosimetry tool here to generate the cumulative dose. Here you can see now a big table that is computed. You can save this also as Excel file. And this table contains one row for each organ that was segmented. Here the kidney in yellow, the liver, the lung, the muscle, and the tumor for each time point. And we have 4 time points here. And the data is visualized here in this graph. So you can see the x-axis is the time, and the y-axis is the dose rate in gray per second. So we have one curve here of the dose rate over time for each organ or tumor that you segmented. And you can see that the tumor accumulation is increasing here and then declining on the 3rd day. But the kidney and liver curve, they have a different shape. So they are higher at the beginning and they are then declining. Then to assess the overall absorbed dose, you need to compute the integral, the area under the curve. And this is summarized here in this tab. You can see here the area under the curve, and the unit is gray. And for the tumor, we have 7 gray, for example, but for the kidney, we have 11 gray. So this is the area under the curve here until the last scan time point. The damage from the absorbed radiation dose does not stop when you stop scanning. So we fit a curve here, this is the dotted curve, for each organ to extrapolate further into the future to allow estimation of the total absorbed dose. And this is shown here in this column. And now here we estimate the tumor to receive 16 gray, but the kidney gets 18.7 gray and the liver 12.7 gray. So you can see that here the kidney and liver still get quite a high dose and might be the dose limiting organs for this probe. And with this tool, you can estimate the absorbed dose and plan, for example, a therapy for your mice. So you can determine how much you should inject without killing the mouse, but while still treating the tumor in a sufficient way. Yeah, thank you. I hope this is interesting. And I will once more summarize the approach here in this figure. So the initial result is the data that you get from your scanner in a calibrated file format, for example, in megabecquerel per ml. And then this is converted to %ID per ml using our software. Then you compute a dose rate map for each time point using a specific kernel. Then you perform an organ segmentation, and then you get the dose rate map over time and the cumulative dose. Thank you. Bye-bye.